Hello everyone, I am Willie. Today we will be presenting DCGANs, which is Deep Convolutional Generative Adversarial Networks. So Generative Adversarial Network, also known as GAN, is a framework mostly used on image generation, image translation, image synthesis, etc. Basically on image-related tasks. For this presentation, we will focus on the task of image generation, which is the most common one. So the ultimate goal is to train a network G, which represents the generator, such that given an input feature represented by Z, it will be able to generate images from the distribution of the training dataset. A very simple example is like this. We first sample a bunch of Z, which is known as the latent feature vector, from the normal distribution. And then we feed all of these Z's to the generator so that it gives us the results of a bunch of different images from the distribution of the training dataset. In this case, it's trained over different kinds of cup images so that it gives us cup images. If you train it over like a set of vehicles, then you get vehicle images. If it's trained over a data set of animals, then you get animal images. So, but how do we train a generator? Like, how do we train something that maps just a simple vector to an image? We will have to take a look at the structure of a GAN. There are actually two different kinds of components inside the framework of GANs. The first, of course, is the generator. So the generator is the generative model. The input Z is going to be sampled from the normal distribution, and the synthetic images, denoted by X hat, is going to be the output. So the goal of the generator is to produce these synthetic images such that the distribution of these results is as close as to the distribution of the training data set as possible. But then the generator alone only creates random noise. We need to have a guidance to guide the generator to generate images that are ideally from the training data set. So that's where the second component, the discriminator, comes in. The purpose of the discriminator is to evaluate the quality of the generated images. So the discriminator is essentially a binary classifier. It's going to distinguish the real images and the fake images. So the input is going to be a mixed set of images that are sampled from the training dataset and those that are generated by the generator. The output of the discriminator is going to be the probability that whether the input image is real. So this actually forms a game between the generator and the discriminator. The generator will be trained to fool the discriminator, which means that if it successfully fools the discriminator, the generated images will be very high quality. Whereas the discriminator is trained to be more skilled at distinguishing real and fake images over time. This is kind of why it's called the adversarial networks, because the generator and the discriminator can be viewed as each other's opponent. So this is the diagram of how the entire network is trained. We first sample a bunch of real and fake images. The real images is going to be sampled from the training dataset, and the fake images from the generator. We then feed these two different sets of images to the discriminator, and then the discriminator is going to tell us whether the image is real or fake. So every time the discriminator gives us a result, we can compute the loss for the discriminator and the generator with their corresponding loss functions, and then we can use this loss to update the discriminator and generator accordingly. Depending on the stage you are currently in, you would either update the generator or the discriminator.
So to see how the discriminator can actually guide the generator to generate images that forms a distribution close to the training dataset, we have to take a look at the loss function, which is this guy over here. The first term represents the probability of the discriminator correctly classifying real images. The second term refers to the probability of the discriminator identifying fake images. So the entire loss function actually represents the correctness of the discriminator, which is why we try to maximize the loss function when we train the discriminator, even though it's called the loss function. And you can see that during the optimization process of the parameters for the discriminator, which is theta sub d, we do gradient ascent like this. As for the generator, we try to minimize the second term in the loss function because we want to fool the discriminator as much as possible, meaning that we want the discriminator to be unable to tell fake images from real ones, which is this term over here. And this is basically the two rules for the optimization of the two components inside GANs. So this slide shows how the general training works for GANs. During the training process, we would first train the discriminator by fixing the parameters of the generator and minimize and maximize the loss function. So at this stage, we are just trying to improve the discriminator so that it's going to be able to tell fake images from real ones. So after we've improved the discriminator good enough, we would now switch the target to train the generator. So during the second stage, we would fix the parameters of the discriminator and then minimize the loss functions by updating the parameters of the generator so that it's going to be able to fool the discriminator. So after doing this, we would repeat the two different stages over and over again until we achieve the optimal point, which is P sub z equals to P sub data. This means that at the optimal point, we would find out that the distribution of the results generated by the generator is going to replicate the distribution of the training data set. And it's pretty hard to tell that this would actually work for the method provided here. We have to first prove that the global optimality, which is P sub z equals to P sub data, actually exists and is unique. We also have to prove that by training in this kind of way, the generator will actually converge to the distribution of the training data set. And these 2 points are mathematically proved in the original paper of GAN, but I'm not going to go into the details here because that's kind of not the purpose right now. If you are interested, you can refer to the paper that we've listed in the reference slide at the end of this presentation. So that's pretty much it for the introduction to GANs. We will now continue on to the DCGAN.
Hi, I'm Mingxian, and I'm going to talk about our main topic, unsupervised representation learning with DCGANs. DCGAN is an improved version of GAN. DCGAN actually is a set of neural network architecture topology constraints we will mention later. The major reason to develop DCGAN is to find a method to build good image representation from unlabeled dataset through unsupervised learning process. The image representations makes a simpler and more abstract form of image, such as we reduce the dimension of image into a vector. A good image representation should embed the feature information of the original image. In addition, the learned image representation distribution can also be used to generate new natural images. Therefore, the idea is to train GANs and then reuse parts of generator and discriminator networks as feature extractor for supervised tasks such as image classification. The problems faced by traditional GANs are first, how to build a stable architecture of GANs. It is found that GANs are hard to train and the generators often produce nonsensical outputs. Second, how to visualize and explain what GANs learn to demonstrate that the feature extracted by GANs is reasonable and reliable. The contribution of this paper are first, they propose and evaluate a set of constraints on the architecture topology of convolutional GANs that make them stable to train in most settings. This class of architectures is defined as deep convolutional GANs. Second, they use train discriminators for image classification tasks and obtain competitive performance with other unsupervised algorithms. Third, they visualize the filters learned by GANs and empirically show that specific filters have learned to draw specific objects. Fourth, they showed the generators have interesting vector arithmetic properties. By addition and subtraction of the vectors, they can easily manipulate many semantic qualities of generated images. What is the architecture guidelines for stable DCGANs? First, replace any pooling layers with strided convolutions in discriminator and fractional strided convolutions, which is used in generators. The reason to do this is to allow the network to learn its own spatial upsampling and downsampling. Second, remove fully connected hidden layers for deeper architecture. The strongest example of this is global average pooling, which has been utilized in state-of-the-art image classification models. However, they found global average pooling increased model stability but hurt convergence speed. So they choose a middle ground by directly connecting the output of generator and the input of discriminator. Third, use special norm in both the generator and the discriminator. This helps deal with training problems that arise due to poor initialization and helps gradient flow in deeper models. It is also critical to prevent the generator from collapsing all samples to a single point, which is a common failure observed in GANs. However, directly applying batch norm to all layers resulted in sample oscillation and model instability. Therefore, they didn't apply batch norm to the generator output layers and discriminator input layer. Fourth, use ReLU activation in generator for all layers except for the output, which uses 10. Use leaky ReLU activation in the discriminator for all layers. It is observed that using a bounded activation allows the model to learn more quickly to saturate and cover the color space of the training distribution. Here, I briefly go through what is fractional strided convolution not used in DCGAN's generator. A more well-known name is transpose convolution. Although there's a slight implementation difference between transpose convolution and fractional strided convolution, their concepts are same. Use convolution to do upsampling. However, transpose convolution is different to deconvolution in mathematics. This figure shows how transpose convolution works with stride of 1. At first, the kernel is on the top left corner, and the input 0 times with each values in the kernel, and then put in a corresponding position of the output feature map. And then because the stride of is 1, so the kernel will move 1 pixel each time and repeat the same process. Finally, these all values are summed up to form the final output feature map. Okay, this example shows how the transpose convolution works with stride of 2. We can see that the kernel moves 2 pixels each time, and the overall procedure is pretty like the normal convolution, but we just change how many values to multiply in input feature map and kernel. And normal convolution, we multiply all the input with single kernel value. But in the transpose convolution, we multiply one input value with all the kernel pixel value. And so After we talk about the architecture of DCGAN, this is an example of DCGAN generator. The input is a 100 dimensional uniform distribution Z. It is project to 1024 4 times 4 feature maps by matrix multiplication, and then a series of 4 fractionally structured convolutions, then convert this high level representation into a 64 times 64 pixel image. So after generator, we can transform the Z into an image. Note that there's no fully connected or pooling layers are used. Here is some detailed training settings mentioned in the paper, including preprocessing method, batch size, initialization method, activation function, and optimizer and learning rate. Okay, they use 3 datasets to evaluate the model. First one is LSUN. And the first one is LSUN. The second one is faces, and the third one is ImageNet 1K. LSUN has many images, but some of them are pretty similar. So they train an autoencoder to find out which image have similar features and eliminate them to do the duplicate. Faces are datasets created by themselves by collecting human face image from random websites. They use OpenCV to draw bounding blocks of faces and ensure the resolution of each image are high. For ImageNet, they perform mini resize center crops to make the image 32 times 32 pixels. There's no data augmentation for all the 3 datasets. To train the GAN, there's a doubt that the generator might just memorize the input data and mimic them. So the model learning fast could have a potential problem that it couldn't produce image that are totally different from the input samples because it just imitate the input data. To declare that, so to clarify that their DCGAN don't have this problem, they show the image of bedroom generated by the generator after 1 epoch of training and generated image after 5 epochs of training. There appears to be evidence of visual underfitting because there are repeated noise texture across multiple samples. Therefore, so the model is not producing high quality samples via simply overfitting training data. After training, how to evaluate the quality of representations given by DCGAN, how to validate the capability of this learning algorithm. The common technique is to apply GAN as a feature extractor on a supervised data set, and then train the linear model on top of this feature. The performance of linear models reflects the quality of these features, these representations of images. Because the better the extracted features can represent the images, the easier for classifier to classify. They perform 2 evaluations. The first is to classify cipher 10, and the second one is to classify SVHN. So in the first evaluation, they first train GAN on ImageNet 1K, use the features from all convolutional layers, and max pool each layer representation to produce a 4x4 spatial grid, flatten and concatenate them to form a long dimensional vector, and then finally they train a regularized linear L2 SVM classifier on top of them to classify cipher 10. The table below is the comparison of different classification algorithms. We can see that the accuracy of DCGAN plus L2 SVM is pretty high. It only loses to the exemplar CNN, which is a technique trains normal discriminative CNN in an unsupervised fashion to differentiate between specifically chosen samples from the source dataset. So because it beats all the other models except example CN, so this experiment demonstrates the domain robustness of the learned feature since the DCGAN was never trained on Cyber 10. In the second evaluation, their experimental steps are same as previous one. Similar dataset preparation, same feature extraction pipeline, and same L2 SVN training. The table shows the comparison of different deep learning classifier. We can see that DCGAN's performance achieved state-of-the-art with 22.48% test error rate. Moreover, they also validate that the CN architecture is not a key contribution factor of the model's performance. They trained a purely supervised CN with the same identical architecture on the same dataset, but get a significantly higher 28.87% validation error rate. So the key contribution must not be the CN architecture, but the extracted feature of DCGAN. To make the experiment results convincing, they investigated and visualized the internals of networks. First, they work in the latent space. It's also called Z space. What it means is that they pick up two Z vectors, do interpolation between them to get another 8 vectors, and then feed them into generator to get images. The results show that the latent space of learned representations has smooth transition. The first row, we can see that a room without windows slowly transform into a room with windows. And the second row, we can see a TV slowly transform into a large window. If working in this latent space result in semantic change to the image generation, such as objects added or removed, then it is a strong evidence to reason that the model has learned relevant and interesting representations. Second, the visualization the discriminator features using guided backpropagation. Supervised CNN result in powerful learned features that act as an object detector. They want to show that unsupervised DCGAN also do the same things. So it can also learn a hierarchy of features. On the right-hand side, we can see that the discriminator activates on typical part of the bedroom, such as bed and windows. Change filter in discriminator focus on important object compared to the random filters. So they manipulating the generator to make it forget to draw certain objects. The output image quality suggests that the generator learns specific object representations for major components such as beds, windows, doors, and other furnitures. So they fit a logistic regression to predict whether a feature activation was on a window and use it to drop all feature maps with weights larger than 0 from all spatial locations. In this picture, we can see that some windows are removed. Some are transformed into objects with similar visual appearance, such as door and mirror. Also, visual quality on the bottom side decrease. Overall scene composition stays similar, suggesting the generator has done a good job disentangling scene representation from object representation. Fourth, they perform vector arithmetic to manipulate face samples generated. If the representation space has reached linear structure, then simple arithmetic operation should work. For example, vector of king minus vector of man plus vector of woman should be equal to vector of queen. So in this figure, we can see that the arithmetic of the vectors actually works. They take an average of the vector of 3D vectors to have a man with glasses, and take another three D vectors, take average to make a man without glasses, and they also get a man without glasses image, and then they do a minor subtraction and addition, and then finally they get a result of woman with glasses, and the center one is the result, and the surrounding 8 image are added with some uniform noise. So the result shows that it's semantically obey the arithmetic. Previous work has demonstrated that conditional generative model can learn object attributes like scale, rotation, and position. However, this is the first time purely unsupervised models demonstrate this kind of ability. Finally, they make face turn from right to left by creating a turn vector from 4 average samples of face looking left vs looking left vs looking right, and add interpolation along this axis to random samples. This also proves that this face is very linear. We can see that the face gradually not only gradually turn from right to left, but also change from one's face into another one's face. To sum up, DCGAN, a more stable set of architecture for training GAN is proposed, and they prove that adversarial networks can learn good representations of images for supervised learning and generative modeling.
So lastly, we'll introduce a little bit on hardware acceleration for GANs. Most of the works on GAN acceleration are focused on the generator part. This is pretty easy to understand because we don't need the discriminator to give us the synthetic images. The discriminator is the component for us to train the generator during the training process. So basically during deployment, the discriminator is just going to be discarded. And secondly, the bottleneck of all the mathematical operations is located at the transposed convolution layers in the generator because it has a lot of inefficient operations. So for example, the zero transposed convolution will first pad the input feature map with a bunch of zeros like this, and then perform the traditional convolution to give us the output feature map. This is very inefficient because, as you can see, there are only 4 non-zero elements. And it's reported that over 70% of the multiplications are wasted. So we all know that the zero transposed convolution causes the checkerboard effect. So there was an improved method, which is the nearest neighbor transposed convolution. It basically replaces the zero elements with the nearest neighbor for the gray parts here. And as you can see, we're not multiplying the kernel with zeros now. So to actually accelerate this, we can take advantage of the repeated patterns to increase the throughput of the nearest neighbor convolution method. And another part of the acceleration would be the uniform accelerator for different kinds of transposed convolution. So basically, most of the works recently employs different computing patterns for different types of transposed convolution. To develop a uniform accelerator architecture for both zero transposed convolution and nearest neighbor transposed convolution would benefit in reducing resource overhead. So that's basically what the Uni OPU does. If you're interested, you can go check it out on the OpenOPU website. So that pretty much concludes our presentation. Thank you very much.